All right, we talked about the quantization of energy, where light can be thought of as little packets called photons, and the energy of each photon can be calculated based on its wavelength or frequency using an equation like this. So then we talked about some of the things that solves, some of the problems that solves with respect to the atom with atomic spectra. So I want to go back a little bit and get more into that kind of weird problem that we talked about, where I didn't put the pictures in the notes, but kind of this issue. If you pass an electron beam through slits, it has the same behavior that you would expect for waves, even though electrons are, we think of as particles. Even if you just do it one electron at a time, you still get that interference pattern. And then if you try to measure it by using light to detect when the electrons come through, that actually collapses and you get that particle behavior again. So it actually changes whether it acts like a wave or acts like a particle, depending on what's being measured there. And so one of the consequences of that is something called wave-particle duality, which is just the idea that any particle can be described as a wave with wave properties. So it can have a wavelength, and it can have a frequency, and it can diffract and refract, and it can interfere constructively and destructively, just like waves do. And then any wave can be thought of as a particle by thinking of it in little packets and photons. So it's sort of like the opposite, or when we take those two things together, we have this idea that everything can be both a particle and a wave and can be described in both ways. So we already talked about how we describe energy as particles with these photons. How we describe particles as waves is something called the Debroglie wavelength, which is just an equation that allows you to calculate wavelength, which is a wave property, based on the mass and velocity of a particle. So the wavelength of a particle can be calculated by dividing Planck's constant by the momentum of the particle, which is mass times velocity. So in this way, you can calculate the wavelength of an electron if you know how much the electron weighs, which we know the mass of the electron, and you know how fast the electron is going, which you can control by electric fields. You can also do this for less reasonable things. So for instance, I think there's a problem here. I think this is from the homework. So you can calculate the wavelength of a baseball. Let's say that baseball is traveling 143 grams, and it's being thrown pretty fast. "95 miles an hour. Now that's definitely a particle, and you would expect that if you threw that towards some slits, that it would either hit and not go through, or it would go through one of the slits or not. But we can actually calculate this and think of it as a wave, so let's try it. To do this, we need mass and velocity, and of course we need them in our normal metric units because Planck's constant deals with joules, which is kilograms, meters, and seconds. So we need to convert that mass to kilograms, which we can do. 143 grams, and there's 1,000 grams in a kilogram. So that's 0.143 kilograms. And then instead of miles per hour, we really need meters per second, meters per second. So 95 miles per hour is 95 miles per 1 hour. So we can convert hours to seconds and miles to meters. There are 60 seconds in an hour.
And 60 minutes?
Oh, you're right. Sorry, 3,600 seconds in an hour. 60 minutes. Sorry about that. And then how many meters are in a mile? Let me know.
Isn't it like 1,760, something like that?
That's yards. That's yards. Yeah, I don't actually know. Let's look it up. See if there's conversion factors in here. Thank you. 1,609. (1,609) meters in a mile. All right, so it's 95 divided by 3,600 times 1,609 is 42.5 meters per second. Okay, so now we've got a mass and a velocity. So the wavelength of the baseball now is Planck's constant, which is 6.626 times 10 to the minus 34 joule seconds. I think I got that number right. Yep. Divided by the mass times the velocity. Does anybody have a nice fancy calculator can deal with all those exponents nicely?
Yeah.
Mind typing it out for me, please?
I got 1.09 times 10 to the negative 34.
Whoop. And that's meters. So that's the wavelength of a basketball, or a baseball. Thrown, remember, it depends on the velocity. So thrown 95 miles an hour, a baseball has a wavelength of 1.09 times 10 to the minus 34 meters. How does that compare with other wavelengths that we've seen? Ideas? What's small? Yeah, what's the wavelength of visible light?
750 nanometers to 400 nanometers.
Yeah, so in the hundreds of nanometers, right? Upper hundreds of nanometers, which is 10 to the minus 7th or so. So this is 10 to the minus 34. So you're talking about trillions and trillions and trillions and trillions and trillions of times smaller a wavelength. So that's why the baseball doesn't appear to have wave-like properties. A baseball doesn't diffract because you can't have two slits that are approximately that far apart, because that would be way smaller than an atom. Yeah, because an atom is about 10 to the minus 10th apart. So the wavelength of a baseball is so small that we could say effectively it doesn't matter that it has wavelength properties. It has them, but they never manifest themselves. Whereas an electron, which is much, much smaller, traveling at a pretty fast speed does have a reasonable wavelength. So there's an example in the book where they do that. They actually do that calculation, and they find that an electron has a wavelength right around the 10 to the minus 10th range, which means it does diffract. And in fact, that's, if you've ever heard of something called X-ray diffraction, which is a powerful analytical technique, that's how it works. Is you shoot, or not X-ray diffraction, sorry, electron diffraction. You can shoot electrons in a tunneling or a transmission electron microscope through a solid, like a crystalline solid, and you can see the diffraction pattern that's caused by the electrons diffracting through the solid, because atoms are about that size. So that is like going through those layers. So the smaller the particle and the less mass it has, the more important its wave features become. And the larger it is, or the slower it is, the more important its particle features become. Okay, let's get weirder. So the other idea here is that the wave and particle nature are complementary. In other words, if there's more of one, there's less of the other. So if one becomes more important, the other one becomes less important. So as we just talked about with the baseball, the particle properties become more important, the wave properties become less important. And this kind of explains the weird behavior of those diffracting electrons, that when we are hitting them with light to measure where they are, we're basically accentuating the particle properties by saying that it has a specific position. And when we're not, then we're accentuating the wave properties by talking about its diffraction and its velocity. So putting all of this together, we get something called the Heisenberg uncertainty principle. Have you heard of this before? Oh, okay. Yeah.
Did you watch Breaking Bad?
I watched a bit of it. There's too much TV now. Just don't have time to Don't you think there's just so many shows? People like this one Game of Thrones that just ended.
Oh,
I'm
yeah.
watching it right now, so I'm spoiled.
Yeah, I don't know. I haven't seen any of it. It's
was
like another
really
thing.
good.
I look at it like, oh, people say it's good, but it's like, 100 hours or whatever to watch the whole
It's a
thing.
lot,
So
yeah.
probably not going to get to that.
I would only watch it at night. It takes a long time.
Isn't Breaking Bad like 10 seasons or something? Is it not pretty long?
So here's the equation form, and then we'll talk about what this actually means. Okay. So the uncertainty principle says that the product of the uncertainty in position and the mass times the uncertainty in velocity, which is the uncertainty in momentum, has to be greater than a specific value, which is Planck's constant divided by 4 pi. So what that means is this delta x and delta v is how well you know that particular value. So if you pinpoint the position of something, that means that there needs to be an uncertainty in its velocity. In other words, you don't know how fast it's going. Because, and then the opposite is true as well. If you know exactly the speed, then you can't know the exact position. The uncertainty in position becomes greater. So that's this idea of balancing. Position is a particle thing, like where a particle is. Momentum is the wave-like thing, like we just talked about with the Debroglie wavelength. So the more you know one, the less you know the other one. So the more deterministic your motion is, the less wave-like it is. So you can see how this kind of only matters in certain situations, because that number, h, remember, is extremely small, 10 to the minus 34. Super, super small. Super, super, super small. So anything that has a decent, anything that you're talking about in a normal everyday life, throwing a ball or something, it doesn't matter, because you're never going to have so much certainty of that thing that it's ever going to approach that limit. Also, the mass becomes so big that that counteracts it as well. But very, very small things or things traveling extremely quickly absolutely do run into some problems with this. And primarily what we're interested in as chemists is electrons. Electrons have a problem here. Because when electrons, if you know exactly where an electron is, then you can't know exactly where it's going. If you know where it's going, if you know like the velocity, that's more wave-like, that's more light-like, then you don't know where it is. And so that's where this uncertainty principle comes from. So the one consequence of that is the idea of indeterminacy versus trajectory. So let's take a look at a picture there that I think explains it pretty well. Not this one, but this is trajectory. If you've ever taken physics, this is what, you can like say that, has anybody taken physics? So have you ever done problems where it's like, you hit a ball at this, it starts out at this velocity, and then you calculate like where it's going to land based on its vertical and horizontal components of the vectors or whatever. Super fun stuff, right? Maybe not so much. But you can calculate that. And we can use this for amazing things, like shooting things into space and knowing exactly when they're going to contact some other planet and then like be able to plan all this out. You can calculate these specific trajectories. And that requires precision in both position and velocity. You need to know where something is. You need to know where it's going to be in a certain amount of time, and you can do that. Well, when you start running up against the uncertainty principle, you can't do that anymore. So for an electron, we can't say the electron is here, and in 2 seconds it's going to be here, and then in 5 seconds it's going to be over here. We can't do that because there's this uncertainty because it's kind of acting like a wave. It's doing other weird stuff. So it's kind of like this. I like this picture because we're going to use it when we talk about orbitals. So in the classical trajectory model, you say, here is a thing, and it is following this path precisely, and it will eventually end up here. That's called trajectory or determinism. In probability distribution, or an indeterminate version of that, would say there is a thing. It has a probability of being found in this area with a certain degree of certainty. And we'd say, like, the lighter the colors become here, the less certain it is to be in that area, the lower probability it has of being in that area. So when we talk about things that run into this uncertainty problem, we're starting to talk about probability. We're saying there's a high probability that this could be here, there's a high probability it could be here, there's a low probability that it's here. So all of the white area outside of that fuzzy part, there's a 0 probability that the electron could be there. Anything that's fuzzy, there is a non-zero probability. The darker it is, the greater the probability that the electron can be found there. But we never say the electron is precisely here, because we can't have that information. That violates the uncertainty principle. I know that's weird. And it's weird because we don't encounter it in everyday Newtonian physics. Newtonian physics works great for anything at the relatively large level. But when you get down to electrons, it breaks down. And that's why we need quantum mechanics to help us out. All right, so back to atoms. So we talked about, and we'll be doing a lab on this on Thursday, we talked about how atoms make this very specific type of spectrum where only certain lines come through. And the Bohr model, Niels Bohr's idea was that it's because the electrons can only be in these discrete levels and they kind of jump from level to level. So when you put energy into an atom, you're pushing the electrons out to the upper levels, and then when they relax back down, the energy gets emitted as light. Energy can either be emitted as heat or light. In this case, it's being emitted as light, and because there's only certain levels, only certain light is being emitted. Now, there's also probably light being emitted from like 5 to 4, and 5 to 3, and 5 to 1, but those are outside the visible spectrum, so that's why we don't see them. So here's a question. If 5 to 2 emits violet light, what do you think 5 to 1 is going to emit? We can't see it. Is it going to be higher energy light or lower energy light? Higher, right? Because it's going farther in energy. It's going closer down toward the nucleus. So it's emitting higher energy light. So what's higher energy than violet? Yes, but there's one in between. We also can't see it. No, microwave's the other direction.
UV?
Yeah, UV, ultraviolet, is higher than violet. So the 5 to 1 transition, in fact, all of the numbers going all the way to 1 end up being in the ultraviolet. And so those are non-visible. We can't see them. What about some of these smaller transitions, like 4 to 3 or something? Why aren't those showing up invisible? Where would those be?
Those would probably be radio wave or
Actually, they're just below the visible light, which is what? You remember? What type is just infrared is? So infra means lower, so infrared is just below red. Ultra means higher, so ultraviolet is just above violet. But remember, those above and below ideas are in energy, not wavelength. The wavelength is inversely proportional. The larger wavelengths are down at lower energy over here, and the shorter wavelengths are at the higher. It takes to what's it doing that? To do these different transitions in the hydrogen atom. Okay. That took a little bit, but let's try this. The principal quantum number is called n. And it describes the energy and size, actually, of an orbital. Let's talk about this word orbital. So in the Bohr model, which you probably have seen in the past, go back up to that. And this was actually what Bohr thought at the time. The idea was that electrons spin around the nucleus much like planets go around the sun. But we know now, and he called those orbits. So there's the first orbit, the second orbit, the third orbit, the fourth orbit, and those are the things that the electrons pass between. But now we know that can't be the case. Any idea, based on what we said a couple minutes ago, why can't electrons travel in orbits? Chris?
because you would know the velocity and the location, so you can't know that, so you just have a probability of it'll be somewhere in the orbit.
Right, exactly. So a planet is deterministic. We know exactly where Saturn is going to be in the entire future, basically, and where it has been for however much of the past. We can calculate exactly the minute and the day and whatever, and know exactly where Saturn's position was, because we know the orbit and we can predict it, and it's deterministic. Because of the uncertainty principle, we can't do that with electrons. We can't say that the electron is here and here. We don't know the path that the electron travels on. So instead of talking about a deterministic orbit, we talk about a probabilistic orbital. So we add that little AL to say that, okay, it's kind of orbit-like, and we're honoring that past idea that they thought it was an orbit, but that's really not what's going on. It's really that the electrons are in these probabilistic areas where we say, okay, well, there's a non-zero probability of finding an electron in this area, rather than talking about an actual orbit. And we'll look at what those things, we'll talk about what those look like in a minute. But let's look at the calculations now. So knowing this principal quantum number, that's going to describe these different levels. And these different levels are the levels, whether you think of them as orbits or orbitals, that the energy thing doesn't change. And the energy of any given orbital can be calculated as, this is called Bohr's constant, minus 2.18 times 10 to the minus 18th joules times 1 over n squared, where n is any integer greater than 0. So those describe the different energies of the orbitals. That equation describes those energies. Notice a couple things. So first of all, it's a negative energy. That's because we kind of set 0 at the top. And so the lower the energy of the orbital, the more negative it gets. When we talk about emitting versus absorbing energy, then we can play with that negative and kind of decide what we're going to use. But in the basic equation, it's like this. This is sometimes known as the Bohr constant or the Rydberg constant for hydrogen. If you graph this out, if you actually calculate these different energies, you get this. Oops. So there's some different values. If you plug 1 in for n, you get the bottom number. If you plug in 2, if you plug in 3, if you plug in 4, those are the numbers you get. So what do you notice as a pattern here? What's happening to the energies?
The higher you go, those energies required.
Right. The higher you go, the levels become closer and closer in energy to each other. Why do you think that is? Physically. So why do the energies have to approach a particular limit? Why can't you just keep having higher and higher energies?
Wouldn't they leave the orbit if the energy continued to increase?
Right. Well.
And
break away from the atom is the big thing. So if you keep promoting electrons to higher and higher and higher levels, eventually you just kick that electron out of the atom entirely, and that's called the ionization energy. That's called ionization. So once you get so much energy, you're going to actually kick that electron out. And that's why you see this behavior of these energy levels. This also describes the different kinds of light that we saw in the spectrum a little bit better. So you notice there's a huge distance in energy relative between 1 and 2. So the transitions where things were dropping all the way down to 1 were emitting much higher energy light, and that was that UV light that we couldn't see. And the ones that are transitioning between ones that are a little bit higher are emitting the lower energy visible or infrared light. Okay. So now if we have, whoops, we're jumping around a little bit here. So if we think about what's happening in that idea of atomic spectra, where you're emitting light from an atom, what's happening is you're putting in electrical energy in the form of a current or voltage, a potential. You're exciting the electron up to an unstable higher energy level, and then that electron is falling back down. And as it falls back down, the light is emitted as energy, or the energy is emitted as light. So if we want to know, since we know how to calculate the energies of a photon, let's say we want to know exactly what color light is going to come out of a particular transition. So let's say we want to answer this question. What wavelength of light would a photon have if it was emitted from an n equals 3 to n equals 2 transition. So we've got an electron and a hydrogen atom that's excited up to the third level, drops down to the second level, and emits a photon. How do we determine the wavelength of that photon? Almost there, almost there. So it doesn't quite work that way because it's on the denominator. So what you got to do is calculate the energy of each level and then subtract them. So let's try that with you since you've got your whiteboards. This half of the class, calculate for n equals 3, and this half of the class, calculate for n equals 2. And then hold up your boards toward each other, and we'll do the subtraction and see what we get. We have numbers?
Yeah.
Okay, hold up your signs so you can see each other's numbers for 2 and 3. So for 2, or you did 2s or 3s? 2s? All right, so 2's got minus 5.45 times 10 to the minus 19th, and 3's got minus 2.42. Times 10 to the minus 19 again, right? And that's in joules as well. All right. So what's the difference between those two? Delta E, the difference in energy from 3 to 2. Now, do we want to end up with a negative number or a positive number here? It kind of depends. So let's go back to our heat chapter. This isn't heat, this is light, but same idea. If we have a emission of light, is that a negative energy or is that a positive energy? If the light is coming out of the atom, that's negative because the energy is leaving. So anytime it talks about emission, you should end up with a negative number. Anytime you're talking about energy absorption, you should end up with a positive number. And if you keep that in mind and compare it to the exothermic endothermic thing, then you don't need to worry about like, oh, do I subtract like final versus initial or initial versus final or whatever. It doesn't matter. Just make sure that your final value reflects what you're actually talking about. We're talking about emission, so we should be talking about a negative energy coming out of the system. So that said, what'd you get for the subtraction? Did we get that one? Negative 3.03 times 10 to the minus 19th joules. So that tells us what? That tells us the energy of what?
Required for it to happen, something to.
Not quite, because it's emission. So it's not the energy required for it to happen. It's the energy of something. It's the energy of the light that comes out of that atom. And more specifically, it's the energy of one photon of that light, one little packet of that light. So how do we actually answer the question then? What wavelength is the photon that has that energy? How do we get that?
Do we need the mass?
We don't need the mass.
Do you use the energy of the photon and set it equal to Bohr constant times the frequency?
Right, right. So we know that the energy of a photon can be described by h nu or hc over lambda. Okay. So if we set that equal to our energy, so go ahead on your whiteboards again, solve for lambda, and then we'll take a look at them. Yeah. So, good question. For this exam, since we've only got a couple days, I'm going to give you all these equations from this chapter. All this stuff is going to be on the exam for you. By the time we get to the final, it will not.
What is the C of HC?
Speed of light, 3 times 10 to the 8th meters per second.
Is it 3 times 10 meters?
Yeah, 2.998. Okay, good. So one thing I didn't think about when we're finding the energy of the photon or the wavelength of the photon, we want to get rid of that negative because it doesn't really make sense to have a negative wavelength. It's true that the energy is being emitted, but if we started with that negative energy value, we would end up with a negative wavelength. So we want a positive energy, like the absolute value of the energy describes the photon. All right, so a 6.56 times 10 to the minus 7 meters. What is that in nanometers?
6.56.
Not quite.
Wasn't it to the 7 nano?
It's 656 nanometers because a nanometer is 10 to the minus 9th meters. So if we have 6.56 times 10 to the minus 7, we have 656 nanometers. Multiply that by 10 to the 9th. You get 656. And that, anybody know what kind of light that is? It is visible light. It's red, yeah. So let's go back up to our spectrum here. That's that line right there that was actually observed in the spectrum.
Is that fair game for the exam? Solve all this and then what color? Like if it's, say we do figure out it's invisible light,
Oh.
you ask what color that would be. 'Cause I know not
No,
all
I don't think so. I think if I asked you that, I would give you this spectrum. I don't expect you to know what color all the different wavelengths are.
extra credit.
Maybe.
But like, so our final answer is to be in nanometers then?
No, it just depends on the
it's
question.
okay.
Yeah, wavelength could be any distance measurement.
Okay.
It's just that when we think about light, like especially visible light, we're usually talking about in the hundreds of nanometers.
Do we have to know all of the nano, all of those? Like
Yes.
one, two, okay.
Yes, you should know how to do those conversions, the metric conversions. Yeah. All right. So one thing that's neat about this, just historically, is there was actually a guy way before Bohr, back in the 1700s, maybe 1800s, named Rydberg, who actually came up with this first and determined, because you can excite hydrogen and you can look at the spectrum, and he figured out this equation and a constant kind of like this one that describes the transitions within that hydrogen atom, but had no theory behind it, had no idea why it was happening. And then it wasn't until over 100 years later when Bohr, I think it was that long later, I don't have that date here, when with Bohr's theory of what the structure of the atom is and the idea of electrons and quantized energy and stuff, that there was fully a theory behind it to help it make sense. Okay, so we know our atomic spectra. Why do you think we do all this stuff for the hydrogen atom and not other atoms or molecules? Because you can also get atomic spectra from other atoms. You can get atomic spectra from molecules. I guess that would be molecular spectra. All those things have transitions. Why do we focus on hydrogen?
I guess, is it because it's the most prevalent in the...
It's not quite the most prevalent. I mean, it is in the universe, I think.
Yeah.
But I don't think that's why. Chris, you want to go ahead?
Like the hydrogen ion only has one electron, so it's easier to track.
Sort of. A hydrogen atom only has one electron. A hydrogen atom has 0 electrons. Or a hydrogen ion has 0 electrons. But yes, that's right. Julia, is that what you can say? Yeah. What do you think happens when you introduce multiple electrons that messes with this?
Things can.
Yeah, so it turns out that you actually can't precisely determine energy levels of electrons in multi-electron atoms because electrons repel each other, and that influences the energy. And going back to this probabilistic thing, if you don't know where all the electrons are, then you can't calculate how much they're repelling each other. And so you can't actually solve these problems for multi-electron atoms because of the uncertainty principle. So modern quantum mechanics, which is used for things like modeling, like a big field now is modeling chemical reactions. Can we have a computer tell us what's going to happen when these molecules or atoms come together instead of actually having to do the experiment and figuring it out? And that's been a major, major problem because you cannot, it's literally a limit of physics that you cannot figure that out exactly. And so now the reason that we've made progress on that is computers have gotten faster and faster, and so the approximations and the probability calculations have gotten better and better. So even though we can't solve it exactly like we can with hydrogen, we can get better and better approximations through various statistical methods. So that uncertainty principle ends up being a big thing when you're talking about behavior of electrons. All right, so then back to those behaviors. What are these orbitals? We're not going to get into the math of it, but electron behavior is described by something called a wave function. Wave function is given by the Greek letter psi or psi, depending on how you pronounce that. And that's just it's just a parametric equation that determines behavior of a wave, like what that wave is doing. If you square that wave function, then you get the probability distribution, because of course a wave function has different phases, and so if you square it, you get what's called a probability distribution, or a probability density of how likely something is in a particular area. So the wave function, we're not going to get into the whole equation of it. It's fun if you like calculus and stuff like that. But it depends on parameters, which, does anybody know what a parametric equation is? It's like an equation, you know how like you can have variables in an equation, like x or y or whatever? Well, you can have parameters, which would be other numbers that aren't variables, but they can only take on certain values, and which values they take on changes the nature of the rest of the equation. So these parameters are what we call, in this case, quantum numbers. We've already seen one of them. We're going to look at the other ones now. So the quantum numbers are n, the principal quantum number, and n can take on values of 1, 2, 3, and so on. So whole numbers up to whatever, however many levels there are. That's the ones we've already talked about. That determines the main energy level and the size of the orbital. L is the next quantum number. And this has a couple different names, but generally we call it the angular momentum quantum number. It can take values starting at 0 up to n minus 1. So that means that if you are in the first principal quantum level, if you're on n equals 1, the only L number that you can have is 0 for that electron. If you're in n equals 2, then your L's can now either be 0 or 1. If you're in n equals 3, then the L's can either be 0, 1, or 2, and so on. So that's the idea of these parameters. It's sort of like you could split these different switches that tell you something about the electron's behavior, but they only have certain values they can take. So the angular momentum quantum number tells us about the shape of the orbital. So if we look at this probability distribution, this square of the wave function that tells us where the electron might be, the n tells us kind of how generally big that area is. The L tells us what shape is it. Is it a sphere? Is it a weird kind of barbell shape? We're going to look at some of those shapes. These different L numbers have been given names also because they are so common. So L equals 0 is called an s orbital. L equals 1 is called a p orbital. L equals 2 is called a d orbital. And then F. Those are the only ones that are really important that contain electrons at the ground state. And really heavy elements, there's the possibility of an L equals 4 level, but electrons tend not to have that. But if it were there, we would call it a g orbital. we'll put that one in parentheses because in our periodic table, we haven't yet studied atoms that have electrons in g orbitals. All right, so some pictures of those orbitals for you, and then we'll talk about what that kind of means. So here's a probability density of a 1s orbital. So this would be the orbital that has an n equal of 1, so the first quantum level, and an L equals 0. That's called an s orbital, and what that means is if you plug in 1 for n and 0 for L into that wave function equation, and you find the probability density, you get a three-dimensional plot that looks something like that. So it tells us that roughly an electron can be found within a sphere of a particular radius, which is shown as r there. And we are not saying exactly where the electron is, but we're saying here is the probabilistic area where that electron could be. So if you graph that as a function of r, this is telling you where the electron is most likely to be based on the radius. And there's a little bit of a problem with this. Does anybody see what the problem is? So as you the 0 on here would be right in the center of the atom, and then as r increases, you're getting farther and farther away. And the graph is showing what is the probability that an electron can be found in any given spot. What's the problem with this?
It never actually hits 0, so it could be anywhere still, right?
That's part of it. That's part of it. Yes. You would expect it to actually get to 0. What else? Looking at this graph, where is the electron most likely to be found?
Dead center.
Dead center, right? Everybody see that? The highest probability is right at 0, at the r equals 0, right in the center. Can the electron be found right in the center of the atom?
No.
Why not?
Because the nucleus is there.
Because of what?
That's where the nucleus
That's where the nucleus is. The electron can't actually be there. So the pure probability distribution here isn't quite right. So we often instead look at something called the radial distribution function, which kind of corrects for the size of the nucleus, and then you can actually find where the real maximum is. And so we would say that the radius of the hydrogen atom is about 52.9 picometers. It's not because that's exactly the cutoff point where the electron is, like in an orbit. It's because that's where the highest probability of finding that electron is. That's the maximum of the radial probability. So when we talk about a size of an atom, there's various ways you can define the size of an atom, and radial distribution maximum is one of those ways. Okay. Also, since the dot thing is hard to draw, you'll often hear you'll often see orbitals described as their surface. So kind of a hard sphere like that. That is meaning to convey that same thing, but don't be confused into thinking that it's actually like a defined shell. That's just a representation of that probability distribution. It's the real thing is more like this, where there is a various probabilities throughout, and there's a region of higher probability that we call the surface. Okay, so that's an s orbital. If we go up into the next level, the 2s orbital and the 3s orbital, notice that they both look like spheres, just like the 1s orbital. And that's because that angular momentum quantum number, that L number, is defining the shape of the orbital. And so any time L equals 0, any orbital that has L equals 0 is going to be called an s orbital and is going to look like a sphere, basically.
Didn't you say for like n equals 2 and m equals 3 that L can't possibly be 0 or 1, and then for 3 it can be...
Right. So there are other possibilities for L that will give us different types of orbitals.
So they're going to give you what L is, or it's going to be...
Yeah, so we'll talk about how we actually ask questions about that in a little bit. But right, so we can say, what are the possibilities for L in this situation? Or we can say, here's an s orbital, what is the value of L? And it must be 0 if it's an s orbital.
Okay.
The only thing that changes between the higher energy s orbitals, n equals 2, n equals 3, and actually every shell has s orbitals, if you kind of open it up and look at that probability distribution, you find these little holes where there is 0 probability of an electron being. And that's called a node. A node is an area of 0 probability. Again, if we look at that total radial probability for the 2s right there, you'll see that the maximum, the radial maximum there is out close to, what is that, about 300 picometers. But then there's also some distribution, or some probability that's closer. But there is 0 probability at that point, which is weird, because that means that an electron can be 300 picometers from the nucleus. An electron can be about 50 picometers from the nucleus. And in fact, it does occupy those areas, but it never actually travels in between. That's a phenomenon called tunneling, where an electron can actually be in one place and then be in another place without having moved through a place that's in between those two, which is weird, right? And there's been experiments where they've been able to show that through actually fairly large areas, like across a campus or something, where electrons can be quantumly entangled even though they're really far apart, which means that they're kind of related to each other.
That's the experiment where they vibrated one electron and they had another
Yeah.
electron vibrate the same.
Yeah, so there's all kinds of weird consequences of what's going on here with these ideas of probabilities and wave-particle duality. If we move to the third shell, same thing, but then you add another node. So the radial probability gets bigger, or the maximum gets bigger further away from the center. As you go up in n, you increase the distance from the center. That's going to become important in the next chapter when we talk about the pull of the electrons and some of the effects of that. And then you add an additional node as well. All right, so that's the s orbitals. So what happens if L equals 2, or 1, sorry. If L equals 1, then we have something called a p orbital. So a p orbital, there are actually 3 different orientations that p orbitals can take. They kind of look like I don't know, 2 balloons tied together, or maybe some people call them kind of like dumbbells. But they have probability distributions on either side of the atom, of the center of the atom, in that kind of shape. And again, there's a node in the middle. So the electron can't pass through the middle because the nucleus is there, but it is still on both sides. So it can be found with equal probability on both sides of the atom. So you have 3 different p orbitals. All of those would have an L equals 1. And this introduces our next quantum number, which is called the magnetic quantum number. That is shown as ML. And this determines the orientation of the orbital. And it can take values of negative L to plus L in steps of an integer. So if L equals 0, ML can only be 0. If L equals 1, ML can be negative 1, 0, or 1. That's plus L to minus L. If L equals 2, ML can be minus 2, minus 1, 0, 1, or 2. So for our p orbitals, L equals 1 means p orbital. Since L equals 1, ML can take 3 different possible values, and that means there's 3 different types of p orbitals, or 3 different flavors of p orbitals, or 3 different orientations of p orbitals, however you want to think about that. Because there's 3 different possibilities for ML, there are 3 different possible orbitals in the p system. and that's what they would look like. They basically look the same, but oriented along the x, y, or z axis. Sometimes those are known as the px, py, and pz orbitals. Because your axes are chosen arbitrarily, like if you're looking at an atom, you can decide where the z, x, y, and z orbitals are. It doesn't matter. So these aren't like absolutely defined. So you can't say this electron is in the py orbital for sure unless you've defined your axes. And so we'll see some of the consequences of that. Really, if you know that an electron is in a p orbital, then you know that its ML can either be -1, 0, or 1, but you can't say specifically like this one is -1 and this one is 0, because you don't know, because the axes are arbitrary.
Two questions. Why, if it's only -1, 0, and 1, then why, if L equals 2, why wouldn't it just be 1 and then 3 if you're doing -1 and then +1? Or are you saying like a negative? It has to be
A
a negative.
negative. So the values of L, or the values of ML always go from -L up to 0 and then up to positive L.
Okay.
So if L is 2, then ML is going to be -2 up to +2 in steps of 1.
Okay, and then why is z-axis, like, 'cause mathematically that's where the y-axis is, so why is it called z, and then why is the diagonal kind of on the origin called y?
Again, because it's arbitrary. So you can decide. A lot of times, sometimes we pick the z-axis as like coming out at us, and the xy is in the plane. Sometimes we think of z-axis as like up and down, and then the xy is in the plane. It's kind of however you want. Generally, in chemistry, if we're talking about molecules, we make the z-axis the internuclear axis, so like the axis that has the different atoms on it, and then the x's and y's are kind of sticking out. But like these are just conventions. It's totally arbitrary how you want to choose your axes as long as they follow the right-hand rule. Okay, and so on with this. So that's ML. And then the final quantum number, MS, is called the spin quantum number. And it only takes values of 1/2 and -1/2 for an electron. So this is basically saying that there are two types of spin. Spin is an internal property of electrons. We think of it as them spinning around and creating a field in one direction or the other. That's not exactly what's going on. It's more just like an inherent property. But it's called spin for that reason. So the spin can either be +1/2 or -1/2, which we sometimes call up or down. Spin up or spin down. So with these four quantum numbers, we can describe the behavior of an electron. And if we take a wave function and we plug in these parameters and then we square that wave function, you get the probability distribution of that orbital. So if we move on to look at the the d orbitals, we start to get a little bit weirder. Again, there are 5 d orbitals because there are 5 possible values of ML when L equals 2. D orbital means L equals 2. So ML can be anything from -2 to +2. Now these orbitals don't seem to differ just in orientation. They also have there's this dz squared orbital down here that has a little donut around the center, which is kind of a weird looking thing. But again, we can't assign any one of these to specific ML values. These are the 5 possibilities that are represented by the 5 ML values, but they don't correspond one-to-one with those specific values. And then it really gets weird when we move into L equals 3 and start looking at the F orbitals, which have all kinds of crazy shapes. Again, those are the probability distributions of where you might find an electron that had a value of L equals 3 and ML anywhere from -3 to +3.
So how would we be asked a question like this on the exam?
Good question. Let's look at that.
Like, are we going to need to know that one F orbital is F, X, Y, and Z, and then the other F
No,
orbital is
no.
X squared -1?
No, you won't. But we need more pages. Hold on. All right, so how do we ask about quantum numbers? Well, we can do things like this. Which orbital or orbitals cannot exist? 1s, 2p, 4s, 2d. So those are all descriptions of orbitals. Because you're given a number and a letter, this tells you both the principal quantum number and the angular momentum quantum number. So let's actually write down those numbers, because I think that'll help lead us toward the answer. So in a 1s orbital, n equals 1 and L equals 0. The 1 gives us the 1 and S gives us the 0. For a 2p, n equals 2 and L equals 1. For a 4s, n equals 4 and L equals 0. And for a 2d, n equals 2 and L equals 2. Because again, L can be 0. 0 is S, 1 is P, 2 is D, 3 is F. You should know that for the test.
Can you read that one?
Yeah, it's right here. So L is 0, or 0 is S, 1 is P, 2 is D, 3 is F, 4 is G. So SPDF. What? Sure, write your answer on your whiteboard. Which one do you think cannot exist? One or more cannot exist. Whichever ones you think cannot exist, write on your whiteboard. And let's see.
Bless you.
All right, everybody got one or two or however many? Let's see them. What'd you pick? 2D, 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 2D. So everybody's pretty sure about the 2D. What's wrong with the 2D? Yeah, Jen.
The L has to be n minus 1, that's like the max.
Right, the highest value for L in a given n level is n minus 1. So if the n level is 2, then that only allows for L of either 0 or 1. Some people also said that the 4s cannot exist. What's wrong with the 4s? Nobody wants to defend that one? Okay, well, I guess that's a good choice, because that one is good. 4s is fine. Because L of 0 can exist in any of the shells. And so, in fact, every quantum level can have an s orbital. All right. Here's another way we can ask about quantum numbers. Which is a possible set of quantum numbers for a 3D electron? And so I'm going to give them like this: N, L, ML, MS. I'll give you a couple different possibilities. Okay, here's your 4 possibilities. Which is a possible set of quantum numbers for a 3D electron? Have we got an answer? What are you going with? Got whiteboards?
30 more seconds.
30 more seconds. C's. Great, nice. How'd you know it was C? Yeah, do it.
So I was able to figure out all of them but the last one, so I just did it by process of elimination. So can we go over the M of S?
Sure. So let's go through all of them just for anybody who wasn't sure. A, what's wrong with A? Couple problems. So yeah, one is it couldn't be a d orbital because it's not L equals 2. Also, there is no n equals 0 level because it starts at n equals 1. So there can't be an n equals 0. For the second one, that one all makes sense up until the ML. ML is has to be -2, -1, 0, 1, or 2. So it can't be -3, so that doesn't work. C is the answer, because a d orbital is defined by n equals 3, or a 3D orbital is defined by n equals 3 and L equals 2. And as long as the others are within the possibilities, then it's good. Within the possibilities means ML has to be -2, -1, 0, 1, or 2. And then MS has to be either +1/2 or -1/2.
So we don't actually have to know, like, if it's +1/2 or -1/2. It'd just be like if you gave us a third or a fourth instead of 1/2.
Right.
That's not possible.
Because you can't know.
have to know.
There isn't like, it's not like +1/2 means this thing and -1/2 means this thing. Those are just two possible numbers, values that the electron can have.
So if it has all the other correct properties, then it's
Yes,
just gonna be
as long as
one
it's
or
+1/2 or -1/2, then you're good.
So it could be
Um,
like no solution.
Yeah, so D then is wrong because the L value is too high. This would be an F orbital, and also wouldn't be possible within the n equals 3 level. All right, so that's quantum numbers. We'll stop there for now. Let's take a break, and then we'll come back and talk about some of the consequences of this stuff in terms of actual properties of atoms and elements. Hey, hold on. I'm gonna-
So, I was trying to do the like charge that Heisenberg.
Yes.
And okay, I don't get like what I'm doing wrong. So like for this problem,